Okay, I'm going to go ahead and start. Right, today we'll continue our review, and I'm going to move on to chapter 10, which is on the structure and synthesis of alcohols. Okay, I want to make sure that I'm on screen. So I'll make a mark here. And another mark over here. Okay, so take out some paper and something to write with. Okay, we'll start out with alcohol nomenclature. Okay, so draw pentan 3-ol. Right. Okay, so pentane, 5 carbons. The alcohol will be on carbon number 3. Okay. About hex 1-ene 3-ol. Okay, so we have 6 carbons. Right, double bond between 1 and 2. And alcohol on 3. Okay, so this would be an example of an allylic alcohol. All right, name this compound. This would be cyclopentane, 1,2-diol, and it would be cis. Cis cyclopentane, 1,2-diol. Okay. Okay, name this compound. All right, so this has 6 carbons. It's hexane, and SH would be a thiol, so this is hexane 3-thiol. Okay, the next one would be this compound. Okay, name this. Okay, so this is a benzene ring. Okay, so this is phenol. The OH is automatically on number 1 since it's the highest priority. And so this would be 4-tert-butyl. Phenol. Okay, if we don't have the benzene ring, then it's not a phenol, but it's a cyclohexanol. So this is 4-tert-butyl cyclohexanol. Okay, last year, I know there was a lot of cases where students were mixing up phenol and cyclohexanol. Okay, the next one is 4-mercapto. Butan 1-ol. 4-mercapto butan 1-ol. Okay, so butane is 4 carbons. Okay, so the alcohol takes priority by IUPAC rules. So it's on number 1. And then a mercapto is a thiol as a substituent. Okay, so that's 4-mercapto butan 1-ol. Right, the next one is 2-phenyl phenol. 2-phenyl phenol. All right, phenol is this. And then phenyl is a benzene ring as a substituent. This is 2-phenyl phenol. Okay, we haven't covered carboxylic acid yet. We'll cover that next semester. But if we have both carboxylic acid and an alcohol in the same compound, carboxylic acid takes priority. Okay, this is 4 carbons, so this is butane. It's butanoic acid. Carboxylic acid is automatically on number 1, and so this would be 4-hydroxy. 4-hydroxy butanoic acid. Okay, we won't see too many of those this semester, but we will next semester. Okay, those groups that are higher priority than the alcohols include ketones, aldehydes, esters, and carboxylic acids. Right, a lot of alcohols are known by their common names. Okay, butan-2-ol is also called sec-butyl alcohol, for example. And okay, 2-methylpentan-1-ol. I'm sorry, propan-1-ol. 2-methyl. Okay, got too many carbons there. 2-methylpropan-1-ol is also known as isobutyl alcohol. Right, this is propane 1,2-diol. It's also commonly known as propylene glycol. I'll go ahead and write that down. Propylene glycol. Right, alcohols are capable of hydrogen bonding, and so this affects some of their physical properties. Okay, for one, alcohols have higher boiling points than many other functional groups, except, for example, carboxylic acids and things like amides. But most other functional groups of similar molecular weight, such as ethers, amines, thiols, a variety of other functional groups, higher boiling points. Also, because of hydrogen bonding, smaller alcohols are completely miscible in water. And when we get up to about 4 carbons, then solubility starts going down. The larger the alkyl group, the less soluble the alcohol becomes. Okay, so methanol, ethanol, 1 and 2, propanol are all miscible in water, so is tert-butyl alcohol. Solubility goes down, and by the time we get to 1-hexanol or hexan-1-ol, it's only about 0.6% soluble. Okay, be familiar with the properties and uses of some of the commercially important alcohols. For example, methanol is is a common solvent. It's used as a fuel in certain racing cars. It is also used as a gas line antifreeze in products like heat. Okay, ethanol is produced from the fermentation of starches and sugars. And it's used in, well, it's found in beverages, alcoholic beverages. It's used as a fuel and a solvent. Proof refers to twice the percent ethanol by volume. Denatured ethyl alcohol is ethyl alcohol that's been deliberately made poison in order to avoid paying or charging excise taxes. Propan-2-ol or isopropyl alcohol is commonly used as rubbing alcohol. Right. Most alcohols are less acidic than water. Phenol is 100 million times more acidic than cyclohexanol. Okay, so here's phenol. Its pKa is 10. Cyclohexanol, its pKa is 18. Okay, and the reason can be summed up in one word: resonance. Okay, when we form the conjugate base, cyclohexanol, the negative charge is not delocalized. Okay, it's fixed on that oxygen, doesn't go anywhere. In the case of phenol, here's the phenolate ion. Okay, so we've got these four resonance structures. Okay, so the negative charge can be delocalized all the way around the ring. Okay, so delocalization of electrons is a stabilizing phenomenon. Okay, besides resonance, okay, one other thing that increases acidity is if there's nearby halogens. Okay, so 2-chloroethanol is about somewhere not quite 100 times more acidic than ethanol, but trichloroethanol is more than 1,000 times greater in acidity than ethanol. Okay, so here's cyclohexanol. And if we react that with K, potassium metal, we can make the conjugate base. Potassium loses an electron, and then we produce bubbles of hydrogen gas. Hydrogen gets reduced. Okay, besides potassium, you could use a stronger base. You could use something like potassium hydride. Okay, stoichiometry is a little bit different, but you'd still get hydrogen gas. Sodium hydroxide would not work very well. This has a pKa of 18, or this one does. Water is 15.7, so water is a stronger acid than cyclohexanol. Okay, so alkoxide ions are commonly prepared from active metals, sodium or potassium. Weaker acids like cyclohexanol and tert-butyl alcohol, it's more usual to use potassium than sodium since potassium is more reactive. Okay, if we had phenol instead of cyclohexanol, okay, you actually wouldn't want to use sodium or potassium because that would be really reactive and you're producing hydrogen gas. So instead, we could use sodium hydroxide. Okay, so this works very well. And we produce water. Sodium is just the counter ion here. Okay, so phenol is 10 for its pKa, water is 15.7. Okay, so this works because water is a weaker acid than phenol. Okay, write down the mechanism for this reaction. Okay, this chapter is all about alcohols. Okay, this was also covered earlier in chapter 8. Okay, water is not acidic enough or electrophilic enough for the alkene to attack, so we need a little bit of acid catalyst. So this will attack hydronium. Right, Markovnikov's rule. As the rich get richer, there's 2 hydrogens on carbon number 1, none on carbon number 2. Okay, so we form a tertiary carbocation. Water comes in. Right, and this would give us tert-butyl alcohol. Okay, plus we would get hydronium ion back. Okay, so show how you would get this product. So this will start out the same. Okay, we'll have a methyl shift. Okay, this is a secondary carbocation. And then this is now a tertiary carbocation. Water would attack. Okay, so that would, last step would be removal of a proton, and we would get this product. Okay, so that would be 1,2-dimethyl cyclopentanol. Okay, we can avoid rearrangement by using oxymercuration, demercuration, mercury 2-acetate. Draw the product on this one. Okay, borane THF and then H2O2, OH minus. Okay, what would the final product be? Right, this would be an anti-Markovnikov formation of an alcohol. Okay, so we have 2 hydrogens here, 1 here. Okay, so this would be our product. Okay, hydrogen, in this case, would go to the side that has the fewest hydrogens instead of the most. Okay, and then you would name this as 2-cyclopentyl ethanol. All right. Okay, how would we carry out this syn dihydroxylation? Okay, there's two ways we can do this. Okay, one is OSO4 and hydrogen peroxide, or cold dilute KMNO4. Okay, to make the trans isomer, okay, what we could do is first we could form the epoxide. Okay, we used MCPBA, and then secondly, either acid or base. I think the chapter specifically talked about acid, so we form the epoxide and then we open it up, and that gives us the trans. Okay, in chapter 9, we saw that we could use acetylides and carbonyl compounds. Okay, if we have an acetylide ion, okay, which we can make from a terminal alkyne and NaNH2, and carbonyl, choose acetone. Okay, then when this first step is complete, then we'll add water or hydronium. Right. Okay, this reaction, okay, not only is it useful in that it forms alcohols, but it also forms new carbon-carbon bonds. Okay, another way of accomplishing those two things, forming a new carbon-carbon bond and making an alcohol, is to use a Grignard or an organolithium reagent. So if we start off with bromobenzene, and react it with magnesium and ether, using ether as a solvent, we get phenylmagnesium bromide. Okay, this completely changes the polarity. Here the carbon is partially positive, here it's partially negative. Okay, and I'll choose cyclohexanone. Okay, so we have this ketone. Okay, this will attack the carbonyl, okay, just like the acetylide ion did. Okay, and then when this is complete, okay, then we add hydronium. All right, so this would be 1-phenyl cyclohexanol. Okay, so besides aldehydes and ketones, we can also react Grignards with epoxides, three-membered cyclic ethers. Okay, if we use ethylene oxide or oxirane, okay, that gives us a primary alcohol that's 2 carbons longer than what we started with. If we have an unsymmetric or a substituted epoxide such as this, the Grignard reagent will attack the less substituted side. Okay, this is a really strong nucleophile, and so what is going to govern the rate of the reaction is steric effects. So this is going to attack the less crowded side. So this will attack here, break open the ring. Okay, so we have 1, 2, 3, 4. All right, and then when we add hydronium, oops. Yeah, that's right. Okay, so we got 1, 2, 3, 4. 1, 2, 3, 4. Yeah, I'm missing a carbon on this side. Okay. All right, so that would be 1-phenyl butan 2-ol. Right, so here is pentan 1-ol or 1-pentanol. Okay, how would you prepare this using a Grignard reagent? Okay, and there's two methods that you could use. Okay, we could use ethylene oxide or oxirane, so we could disconnect it here. Okay, so that would leave us with propyl magnesium bromide plus ethylene oxide and then hydrolyze. Okay, so that would add 2 carbons and we get a primary alcohol. Okay, the other way would be to, okay, we locate the carbon-oxygen bond and then we break the next carbon-carbon bond. Okay, so we got 4 carbons, so this would be a butyl. And 1 carbon, okay, we make this a double bond. We got 2 hydrogens here. Okay, so that would be formaldehyde. Okay, so butyl magnesium bromide and formaldehyde. Okay, so there's 2 ways we can make this. So how would you make this using a Grignard synthesis? Okay, so we locate the CO bond, we break the next carbon-carbon bond, and in this case, it doesn't matter which one, because it would all be the same. Okay, so the part without the oxygen, that would be an ethyl. Okay, I haven't said anything about lithium, but we could also use the corresponding lithium. Use ethyl lithium. Okay, and then the other part of it would be this diethyl ketone. Right, so formaldehyde or ethylene oxide would give us a primary alcohol. Any other aldehydes would give us a secondary. Ketone would give us a tertiary alcohol. Okay, I have just a couple more minutes left. What if we have an ester? Okay, this will react with 2 equivalents. I'm going to choose ethyl magnesium bromide. Okay, so 2 equivalents, okay, followed by hydrolysis. Okay, so this will start out the same. Okay, this carbon is nucleophilic. Okay, so it will attack the carbonyl. Okay, but we don't hydrolyze it at this step because having an alcohol and an ether on the same carbon is not stable. So what will happen next is this will push down, kick out OCH3 minus. So we'll have a ketone. And when you're drawing the mechanism, okay, don't draw another arrow from this Grignard. You need to redraw the Grignard. So this will come in, and then after hydrolysis, okay, we would get this. We'd get 3-phenyl pentan 3-ol. Okay, acid chlorides will react the same way as esters. All right, so I'm going to stop there. And when we come back from break, Monday the 30th, I'll continue with reviewing. And Friday the 4th will be your next hour exam. And then for the final exam, I'm planning to prepare that on Top Hat. Okay, so I'm going to go ahead and stop here. Okay, have a good break. And I'll see you on Zoom a week from Monday.